Anybody have questions about what we've gone over? Or don't worry about memorizing formulas, because I'll put those on the exam. The formulas that we'll need. So, any questions?
I imagine we'll be tested over like the two variables of water potential that can be ignored or neglected, like gravimetric and...
Yeah, so gravimetric can't really be ignored, but it can often be neglected.
Yeah.
So that one's, I mean, that's important to know something about that.
Right.
Matrix potential, don't worry about that. I won't ask about that.
So it won't be like, choose all that apply, which of these can we neglect? Matrix and gravimetric.
I don't think I'll ask something. No. I know what happens to this. Yeah, so what are the components that are important? So there's gravitational, which can often be neglected. Why? Because it's only about 1/100th of a megapascal per meter. So if we're talking about, say, cell-to-cell water movement, forget it, doesn't matter. If we're talking about water movement from the roots of a redwood tree up 100 meters to the top, then, you know, maybe it's important. That's 1 megapascal difference in gravitational potential over that 100 meters. So there, it's important. So gravitational, osmotic, pressure. Those are the big three. What are they? So gravitational is the results on, okay, back up a step. What is water potential?
Movement from high to low pressure of water.
The amount
That's
of
an
energy-
example of
Go ahead, Dallas.
Amount of energy required for work?
yeah, the amount of free energy in a bit of water, the amount of free energy that can be used for work. It's the chemical potential of water. It represents the energy that's available in water to do something, like move that water from here to there. The work capacity of water. I mean, those are all sort of thermodynamic terms because it comes from thermodynamic principles. So, and you're right, water moves from moves passively from high water potential to low water potential, from less negative to more negative potentials. And because by doing so, that energy in the water is used for the work of moving the water. And that, so there doesn't need to be any external input of energy. It's a passive process. Okay, so that's water potential. Now, the three components, gravitational, that's the effect on the total water potential. That's due to the position of that water in a gravitational field. So it's like potential energy in physics. And that, the magnitude of that term on the surface of the Earth, or near the surface of the Earth, is about 0.01 megapascals per meter of difference in position in that gravitational field. So, all right, so that's gravitational. Pressure potential is the effect on the total water potential due to hydrostatic pressures or tensions on that bit of water. And osmotic potential is the effect on the total water potential due to the presence of dissolved substances in that bit of water. The pressure potential can be positive or negative. The osmotic potential is always less than or equal to 0. It's always 0 or negative. It's 0 if it's pure water, it's negative if anything's dissolved in the water. So yeah, that's the kind of thing that I think is important to say from these first couple of talks that I was giving. There were other things. Well, anybody else have a pressing question? Or not even not a pressing question? Anybody else have a question?
Are there gonna be any, oh, sorry.
No.
Are there gonna be any, there are papers or any, you referenced a couple of papers in the slides. Are there gonna be any questions on any of the papers?
There may be, if there are, those questions will have been addressed in this set of slides.
In the slides?
Right,
Okay.
there, I won't ask you questions about a paper I just gave you the reference for and
That they're running
moved
out of
on to
paper or
something else.
something. Okay,
Yeah.
okay.
But, for example, that Nanami and Boyer paper, where they looked at all the components in the equation for what governs cell expansion, that's fair, because they spent a fair amount of time in this lecture talking about that.
Okay.
So that's okay, but something I just gave a reference in passing, don't worry about it.
Okay.
Can you like go through the equation where you compare thermodynamic with water potential?
Where I compared what with water potential?
Thermodynamics, you use like thermodynamics to kind of like explain water potential.
Do you have it right there?
Yeah, I do.
Okay, okay.
I just haven't known to ask
Yeah,
question
sure.
on
I can-
Tuesday.
Oh, okay, sure.
This part. I just
Oh,
don't have
okay,
the-
okay, sure.
To relate equal.
Sure. I don't know where in this group that was, but it was, do you remember which set, what was?
The third one is the beginning of water, the lecture where you start talking about water potential.
Okay, I'll find it. Maybe this one.
Yeah.
There it is.
Mm-hmm.
Okay, so this one. And then. Yeah. Okay, so this is the definition of water potential, right? So, this is a general equation for chemical potential. And the water potential is the chemical potential of water. So for this equation, the chemical potential of a substance is equals the chemical potential of that substance in some standard state that's defined, plus RT times the log of what's called the activity of that substance. R is the gas constant, T is the temperature in Kelvin. Ln is the natural log. The activity depends on what the substance you're talking about is. So for example, for water potential, we can write that the chemical potential of water is RT, or is the water potential at some standard state, which we're going to take to be equal to 0, so we can forget about this. And then we're left over with this part, which is RT times the log of something. In the case of water potentials for plant physiology, this term is normalized by the partial mole volume of water, which is the volume of 1 mole of water. It's just a convention that people use to do it, but this is a constant, more or less of a constant value too. And the activity in this case is the relative humidity of the air that's in equilibrium with that bit of water. So it depends on the vapor pressure, things like that. And that's how we define water potential. So we won't, this equation isn't very useful for us in plant systems because It's useful in making measurements of water potential, but it doesn't really help us in describing, say, movement of water from one activity to the other and things like that. So it's just I present it just to reinforce the idea that the water potential wasn't something that people just made up. It comes from physical principles. Well, if you accept thermodynamics, you know, it comes from those assumptions that are inherent in thermodynamics.
Will you provide the gas constant on the exam?
Yeah, if I ask you a question about that, sure, I will. It depends on what units you use, and I think I've got some somewhere. Oh, I know what. Yeah. Yeah, sure. If you need it, I'll give it to you. You don't have to remember that. Yeah, you don't have to remember the values of any constants. So, for example, water has a very high latent heat of vaporization. So, my question to you my potential question to you on a quiz or exam could be something about that, but I won't ask you what's the latent heat of vaporization of water. I'm not going to ask you for memory work like that. What I could ask though is make a statement, water has a very high latent heat of vaporization. How does that fact help plants exist in their environment or something like that? You know, or water has a high specific heat.
Sure.
What is it about plants that this fact, you know, how do plants take advantage of this fact to survive in their environment?
So what I'm hearing is that this isn't a chemistry exam, it's applied the chemistry of water to.
Yeah, and it's not specifically a memory exam either.
Yeah.
So if you have a photographic memory, it'll only get you so far, you know. I don't have to worry about things like that, but, you know, but yeah, I mean, I will try to ask questions, you know, that make you think about, okay, given this, what is it about, how does that relate to how plants work? Those kinds of things.
So is it mostly short answer questions?
Yeah, mostly short answer questions.
So not really about specific things, they're broad questions to encompass a bunch of.
Not really specific things. Although.
Like super specific definitions or something?
I mean, I won't say I'm not gonna ask you a definition, but it's not gonna be heavily definition oriented.
Are you gonna have any figures, graphs, and
Uh-huh.
stuff? We discussed a lot of those.
Trying to think about usually not. I usually don't give you a lot of graphs and ask questions about the graphs. But sometimes I ask you to draw a graph of this versus that, or things like that. You know, sketch the diel behavior of water potentials for a terrestrial plant for leaf water potential for a terrestrial plant on a typical sunny summer day. You know, what does it do? Something like that.
How many questions do you have for an exam?
It depends. So I don't know, 6, 7, 8, 9, 10. Depends on how many parts each one has. So usually 2-3 pages of questions with a lot of blank space for your answers. So it's not like solid questions for 3 pages.
Can we see a dial graph chart?
Of
You wanna see that?
of water potentials?
Yeah. Yeah.
Okay, so if this is time here, right? And this is water potential over here. And this is, let's say, 12 midnight, 6 a.m., 12 noon, 6 p.m. Something like that. Okay. And this is 0 here. 1, 2. Okay, so that's the first thing about making a graph, is labeling your axes and putting units on it. That's important. I think that's important. All right. So, let's assume the plant's growing in well-watered soil, not stressed. So you know that early in the morning, it's going to have a total water potential close to 0. Let's say. Let's just, I mean, of course, this depends on the soil conditions. It could start anyway. But let's first start with the total water potential. The sun comes up, the total potential decreases. The sun starts to go down, it increases, and eventually comes back up here to where it started. So this could be the course of total water potential. The osmotic potential starts wherever it starts. Let's say it starts right here. The osmotic potential decreases a little bit during the day and then increases a little bit as the volume in the cell shrinks and swells. So this might be osmotic potential. The pressure potential is the difference between these two. So if this starts at -1.5, this one starts at +1.5. And this minimum coincides with the minimum in the pressure potential. And so the pressure potential goes something like this. So, you know, you can draw better than I can. Something like this, with everything labeled appropriately, with some values and stuff, that's will be all I would be looking for. And exactly where these are doesn't matter so much, although for a living and if I were to ask, this question, I would say, you know, identify what cell in the plant you were talking about. This may be appropriate for a living cell in the leaf. Okay, so like I said, the exact values don't matter, but what does matter, since it is a living mesophyll cell in the leaf, the pressure potential is always positive or 0. The osmotic potential is always negative, and the total potential is negative. So, you know, if this were labeled as osmotic potential, you know, that's not right. Or if the total potential was positive here and did negative, you know, that's not right. But aside from those types of things, the exact values don't matter.
So,
So,
if you were to ask about the gravitational potential in this graph, it's just gonna be a straight line, or no?
yeah, although I wouldn't ask about that.
Okay.
Yeah, but yeah, it probably would be straight line, yeah, somewhere. But then you'd have to know where that cell was in relation to where the gravitational equals 0. And so, I mean, could be here, could be here, could be, anyway, but yeah, it would be a straight line, right?
How would that graph differ if it was not stressed, or if it was stressed?
Okay, if this was a stress, maybe make it really confusing by putting it on the same graph, right? So if it were stressed, let's say, probably the total potential wouldn't come to near 0 here overnight. It would come to, let's say, down here somewhere. So the total potential might do something like this. Osmotic potential probably would start more negative than this. Oh my goodness, how am I gonna do this? Start, let's say, down here. You know, both of these would be more negative. And then the pressure potential, what's this gonna be? Start here, but we're gonna take this off, so that'd be like this. And goes near 0 here and hangs out there a while, and then comes up. So this, the blue is more stressed than the red.
So, the total potential somewhere almost equals to the pressure, to the osmotic potential there?
It is here, and that's when the pressure is 0.
0, so
Yeah, right here. Because we know the total.
plasmolysis.
Equals the pressure plus the osmotic.
Mhm.
So anywhere along this graph, this has to be true. So I may not have drawn it exactly right, but that's what I tried.
And if the stress keep happening, the
Yeah.
total water would be lower than the in the beginning of the graph, so it would be
Yeah,
going
yeah,
down and down.
yeah. So over time, that's a great point. That's what I was gonna say. So as the soil dries out, this value gets more and more negative at the beginning of the day as the soil dries. Because that's as good as the plant can do, is come into equilibrium with the total water potential in the soil over the volume of the roots that the plant has. It can't have a water potential that's less negative than that soil water potential. Otherwise, the water would move from the plant into the soil. And that, I mean, that can happen, but that's, because that can happen, the soil determines the starting point of this pre-dawn water potential.
This isn't gonna be on the test, but, and it's probably not really your field of study, but I'm thinking of cactus when we're thinking of, you know, reverse movement of water from the
Yeah.
plant to the soil. They have to have adapted something to stop that, right?
Cactus?
Yeah.
No.
Oh, it happens with them too.
No.
And-
No plant has that.
A valve,
Above?
like a valve that will not let water go back. You mentioned
Oh,
that.
a valve, no, yeah, no,
You
there's
mentioned
no valves and no check valves, no one-way movement of water. Cactus does, in fact, there have been some interesting studies by ecologists in Utah, Jim Elringer and some of his colleagues, where, okay, here's what can happen. Here's what can happen. That speaks to your point right there. Okay, so here's the soil surface. Let's say we have a shrub growing in a semi-desert environment, right? With its roots down here below soil surface. Well, a lot of times when the soil dries, it dries from the surface down. So it's very dry here and it gets higher water content the deeper you go in the soil. And for a plant like this shrub that's rooted over a volume of soil whose water potential is such that it's dry on the top and more moist down here, you may have water movement from the soil into these roots down here, up the root, and then when it gets to this dry region, out of the root into the soil. And so
It's almost
this,
using it as an advantage,
using it as,
almost taking it to advantage.
yeah, well,
Almost.
not necessarily this plant, but yeah, others.
Yeah.
So they call this hydraulic lift. So the end result is you're transferring water from this part of the soil to this part of the soil. You can have other plants that are growing in association with this shrub that only have roots here that can take that water that comes out and use it for themselves. Sometimes they call these nurse plants.
But in turn, those nurse plants will be shading the soil, so it wouldn't be evaporating so quickly.
Yeah, and this shrub is shading the soil too, some, and these may be growing under it. But yeah, this hydraulic lift is enough to allow these plants to survive, whereas if this thing wasn't here, this soil would be dry, and this thing wouldn't make it. So and using stable isotopes and things, people have shown that this, in fact, is happening in these dry environments with dry soil and more moist soil deep. So the survival of these plants depends on this thing moving water within the soil profile. And that happens because there's no valve, there's nothing to stop the water moving from the root into the soil if the soil is dry, if the soil has a lower water potential than what's in the root.
What would be the method of transport in that case where the water is coming out of the roots to the dry soil?
What would be the?
Transport method.
So it's,
Just the fact of leaving the roots.
it's a difference in the,
Wouldn't that be passive?
yeah, it's passive movement, right. And it's due to differences in water potential. But, I mean, to answer the question, we have to consider something about the root and where the water is coming from. If the water is coming from the xylem in the root, and I haven't talked so much about this, but around the vascular system of the root is a group of cells called the endodermis. And the endodermis is interesting because of the way it's made, it blocks the apoplastic movement of water. So any movement of water into the root xylem or out of the root xylem into what's called the cortex of the root, these cells out here, for that water to move, it has to cross a membrane. In that case, it's the difference in total water potential that's driving things. So this this equation, right, for water movement, something like that. Across a membrane, it's the difference in the combination of the pressure and the osmotic components that's driving the water movement. If the water is coming from the cell walls of this cortical cell here, out to the soil. It doesn't have to cross a membrane. And then it's moving in response to differences in pressure potential. So it depends on where the water's coming from to get out to the soil as to exactly what is driving it, that water movement. In that case, we have this equation, right, where the driving force is just the difference in pressure.
So there's no apoplastic movement between the vascular system and the root and the soil itself?
There's no apoplastic movement between the vascular system in the root and anything outside that
Yeah.
vascular system of the root, into these cortical cells, into the epidermal cells, into the soil. The water has to move symplastically to cross the endodermis. It's because these endodermal cells are highly suberized, so they have this waxy coating all around them that blocks water movement. It's like they're covered in wax, and water can't move through them. And in fact, that's very interesting because all vascular plants have that anatomical feature. Every single one of them. They all have a highly suberized endodermis that blocks apoplastic movement of water. So, okay. These are really good questions.
Can you just summarize like the difference between diffusions and convection?
Okay, so.
And which circumstance the plant will pass the diffusion and which?
So convection is this equation, this mass flow that's driven by, the driving force is difference in pressure potential, is the pressure potential gradient. So you have a difference in pressure and the fluid moves because of that difference in pressure. This works only when you don't have a membrane to cross, like a tube or capillary or within a cell wall that's made up of a bunch of little spaces where the water can move. And here's the equation. This is the driving force for the movement, this difference in pressure potential. And this is convection. Sometimes it's called mass flow. Okay, so that's that. Diffusion, what just, I can't remember the symbols I used. Let's say diffusive flow is, I think there might be a negative sign there. Diffusion coefficient times a difference in concentrations. Diffusive transport is written in terms of the substance that's diffusing. So like sucrose diffusing in water. That movement of sucrose, that diffusion of sucrose in water, depends on the difference in concentration between 2 points, between here, A and B, right? And so we need to know the sucrose concentration here at point A, and the sucrose concentration here at B. And this difference in concentration equals concentration of sucrose, let's say at B minus sucrose concentration at A, right? Depends on that difference in concentration. That's the driving force for the movement of that sucrose in water. And then you have a diffusion coefficient that's just relates to the size of the molecule that's diffusing and the nature of the fluid that it's moving through. So it's different for air than it is for water or for methanol or for anything like that. So diffusive flow is due to a different, usually diffusive flow, we're talking about movement of a molecule in a fluid. Water, for plants, water or air. Another example Okay, so that's an example of diffusion. Another example of diffusive flow. Maybe I get rid of this screen. Everybody knows this thing. Another example of diffusive flow is the movement of CO2 from the atmosphere into the leaf in the process of photosynthesis. So if we have the inside of a leaf here with a cell that's with chloroplast that's doing photosynthesis, we have CO2 moving this way into that cell. This movement of CO2, once we get within the leaf boundary layer and in the air spaces inside the leaf, is a diffusive movement. It's because the CO2 concentration in the air spaces of the leaf is less than the CO2 concentration in the ambient air. So this may be some concept. We may have, say, 400 parts per million CO2 out here, whereas inside the leaf, it may be 120 parts per million CO2 concentration. So because of this difference, the CO2 will diffuse from high concentration to low concentration. Passive movement this way. Okay. Simultaneously with that is diffusion of water vapor out from high concentration of water vapor inside the leaf to low concentration of water vapor in the air. And we can write equations for this that say net CO2 assimilation rate for the leaf is equal to the total leaf conductance for CO2 times the difference in partial pressures of CO2 between the air and the inside of the leaf. So here's the driving force for this diffusive flow of CO2, the difference in concentrations. And then there's a term that's analogous to the diffusion coefficient, but this time written in terms of a conductance that represents how easy it is for CO2 to diffuse through this pathway between outside and inside. And we can write a similar equation for a water vapor, where we have the total leaf conductance for water vapor times saturation vapor pressure, the leaf temperature, minus the air vapor pressure, divided by the total pressure. So again, here, this difference in water vapor concentration inside and outside is the driving force for that diffusive flow out of the leaf. And then there's a conductance term of how easy it is for the water to move through the air. So these diffusion kind of equations, there's sort of a very simple representation of there. These are specific examples of that movement, written in terms of the thing that's diffusing, CO2 or water vapor, and taking something of the ease with which these substances move through whatever fluid they're in to get where they're going. So, to summarize this long, involved answer to the question, what's the difference? In diffusive flow, the movement is in response to a difference in concentrations in the substance that's diffusing. In convective flow, the movement is in response to pressure differences in the system. So in water, if water's moving, it's a difference in the pressure potentials, that's the driving force. Diffusive flow is the difference in the concentrations, that's the driving force. So, anyway. And then you have, of course, the membrane, where it's the difference in the total water potential that's important.
So, isn't diffusive flow related to the distance in which it's diffusing?
Yeah, oh, yeah, that's right, that's what I forgot. I knew I didn't have everything on him. Yeah, this is delta C, delta X, it's like a gradient, yeah. There's a distance term, right, exactly. Yeah.
So in the example over there of water leaving the roots in the dry zone of the soil,
Uh-huh,
that's the water going up in the xylem, right? Xylem in the roots.
Yeah, the water, yeah, the uptake of water here, so this long distance transport in the root, from this part of the root to here or to the above ground, happens in the xylem.
Okay.
That's movement in the xylem. And once we're in the xylem, this equation is the important one.
Yeah.
So once we're in the xylem, it's this difference in pressure potential that's moving the water through the xylem. Right.
What about in the phloem? Is there any water loss in the soil dry zone out of the phloem?
Uh-huh. Maybe. But in the, okay, so in the phloem, once we're in the phloem, movement within the phloem, the stuff that's moving doesn't cross any membranes as long as it remains in the phloem. Because the sieve cells, I'll show pictures of this and stuff, but the sieve cells don't have any membranes that have to be crossed to move the water. So once we're in the phloem, just like in the xylem, this is the governing equation. And the driving force is a difference in pressure potentials in the phloem. But to get in the phloem or out of the phloem, you have to cross a membrane, and then this equation becomes important. So, the other difference between movement in xylem, so there may be some water coming out of the phloem, but probably not very much. I don't know. There's more water moving through the xylem than the phloem anyway.
Yeah,
So
you see that.
that's where the big volume of water is. The other difference between movement in xylem and phloem is, in the xylem, these potentials are negative. These pressure potentials are negative, less than zero. There's a tension on the water in the xylem. In the phloem, these pressure potentials are positive. But still, it's the difference in pressure. So in the phloem, we may have water moving from, let's say, a pressure potential of +1 megapascal to a pressure potential of plus 0.5 megapascal, from higher to lower pressures. In the xylem, you may have water moving from, let's say, -1 megapascal to -1.6 megapascals. Again, from higher to lower, from less negative to more negative. It's still a difference in the pressure that's driving that movement. It's just that the sign of in the xylem, these pressures are negative, in the phloem, these pressures are positive. We should have review every day. Good questions. I've got some more questions. Let's get back to graphs. Okay, so an important one is this diel pattern of water potentials in a leaf, let's say, leaf mesosome. Another important one that I've been known to ask in the past is sketch the relationship between relative water content of a cell or volume of a cell and its water potentials and the components of the water potential. So can we do that? This is an important concept to know.
Is that the same thing as a Hepler plot?
Yeah, so for an individual cell, this is the water potential, and here is, let's say, relative water content or cell volume. And x-axis, where, let's do relative water content, 1.9, 0.8, so relative water content. And I could say, megapascals. Okay, sketch the total water potential, the osmotic potential, and the pressure potential for this cell as its water content changes. All right, well, when the relative water content is 1, or the cell volume is at its maximum, that's when the cell is in equilibrium with a total water potential of 0. That's as good as it gets. Highest volume, highest relative water content. So the total potential starts here. As the cell loses water, total potential becomes more negative. The osmotic potential, let's say it starts at -1.5, also decreases as the cell loses water, but not as dramatically as the total potential. So this might be the osmotic potential. The pressure potential is the difference between these, so if this is -1.5, this is +1.5. Again, not drawn to scale, let's say, right? And we come to 0 here, and something like that. This may be pressure potential. So where's the point of incipient plasmolysis on this graph? Right here. This is incipient plasmolysis. And where is full turgor?
Wow.
Right here. Here it goes. Right. So, 24 hours of total water potentials and this cell volume versus water potential. Those are the important graphs from this SOAP that we've covered so far. That what I consider the two most important. Yes.
What is your labels on your analyses?
What is what? This one?
Yeah.
This is the relative water content. Or we could put cell volume on here too, but there would be high volume, low volume, and I would have trouble putting actual numbers on there by the drug. And this is the water potential in megapascals. 0 in the middle, positive here, negative here. So this graph and the daily graph, those are There was another graph that was kind of, semi-interesting, right? But that one was this graph of water potentials in a drying soil, where the soil water potential did this, and then the leaf did this over several days. Remember that? This was the, say, 1 day, 2 days, 3 days. All right, so this shows how the pre-dawn water potential is decreasing as the soils dry out. This graph is I mean, I hope you understand what's on this graph too. But the other two graphs are arguably more important. Who else has a question? Okay, let's see then. Minutes. Other questions? No questions about that? Why concern ourselves about water? Plants are mostly water, carbon gain, water loss. Properties of water. You know, water has a high boiling point, high melting point because of the hydrogen bonding that's going on between the molecules. This helps plants cope with their environment because oftentimes in the temperatures that plants are experiencing here on Earth, we are within this range between the melting point and boiling point, and water exists as a liquid. So that's useful for plants, right? Water has a high specific heat. Okay, there's the value. And this tends to moderate plant temperatures in the face of a changing environment because plants are mostly water. You know, in the Heffler diagram we just put up on the board, over 70% water, and typically 80 or 90% water. So that helps moderate the temperatures. Water has a very high latent heat of vaporization. Here's the value. It takes a lot of energy to evaporate water. Why is that important? Because all the energy that these leaves are absorbing has to be dealt with some way, and typically the two big users of that energy are sensible heat flux, heating this leaf up relative to its environment, or latent heat flux, evaporating water. As long as there's plenty of water around, the stomata are open, the leaves can evaporate water. That moderates plant temperatures. It takes a lot of energy. Whereas otherwise, if they can't evaporate water, like this green plastic over here, the temperatures are way up there. And that would not be good for, like last game, right? They kept showing that thermometer. You see the football game on Saturday? They just kept showing it 100 degrees on the field. Well, if it was a grass field, it probably wouldn't be 100 degrees.
If it was shaded, it wouldn't be that hot though, right?
What, 149?
Yeah.
Well, it might be. This is a radiometric temperature. So this is the temperature of the thing is, the air right above it's not gonna be that hot.
Yeah.
And that's where, you know, you're standing around and stuff. But actually the grass may be that hot, maybe that warm. But it's not, the air is only gonna be 100, not 149 Fahrenheit. At least last Saturday, that's what they kept showing, 100 degrees on the field. But that was the air right above the field. Latent heat of fusion, it releases a lot of energy when it changes state from vapor to liquid. And that's due to the hydrogen bonding in these between molecules. Oh yeah, this is another property of water that's very important for plant functioning. Water doesn't absorb visible light. It is transparent to visible, to this 0.4 to 0.7 micron range here. Which one is water? This blue one. So it doesn't absorb visible, doesn't absorb what your eye see, which is also what plants use for photosynthesis. So water doesn't absorb the light that's ultimately being absorbed by chlorophyll in the thylakoid membranes and used to drive photosynthesis.
How does the water's magnification factor affect light?
You know, that's a good question. And I think there are some plants that have cells arranged like little lenses that focus the light onto certain spots and concentrate that light so that it can be used. I can't give you an example now, but
I'm just thinking in the case of like algae.
yeah, I don't know if I don't know if that has a role to play in aquatic plants. I don't know. But the fact that water doesn't absorb this light, so you can have photosynthesis going on underwater.
Yeah.
Or inside a layer of epidermal cells that don't have chloroplasts but are full of water. That light gets through those cells down to where the chloroplasts are, used for photosynthesis. So that's a very important property of water too. Okay, there we go, that's what's important from this first set of slides. What's important from this one? Oops. Oh yeah, water potentials. Okay, so we talked about this already. Chemical potential of water, the units, components of water potential, the gravitational component, which is about 1/100th of a megapascal per meter. The pressure potential, which for water inside living cells, greater than or equal to 0. For water in cell walls, it's negative. For water in the xylem, can be positive or negative, typically negative, especially if the plant is transpiring. And for water in the phloem, pressure potential is positive. So it can be positive or negative depending on what you're talking about. Osmotic potential, here's an off. This isn't important. CRT, where C is the concentration, R is the gas constant. Here's the gas constant, 0.00832 liter megapascals per K. There's a value per K per mole. There's a value for gas constant. So if you have a solution that has an osmotic potential and you increase the temperature, what happens to the osmotic potential? Gets more negative, decreases, just because of the effect of temperature. If you have a solution and you decrease the concentration of solutes in that solution, what happens to the osmotic potential? Gets closer to 0. So these are the kinds of questions, I could give you this equation and ask you questions like that. What happens to this as one of these things changes? Right? Just something like that. But I won't ask you what is the Van Hoff equation.
So
Another question as
Yes.
far as those constants are concerned.
Yes.
I don't suppose you'll put in a reminder that absolute 0 in Kelvin, no, that's what it is, it's 0 in Kelvin, but in standard Celsius, it would be like -273. So you need to keep, just, I don't know if everybody has,
I mean,
Kelvin
okay.
rates in their head.
All right, and how it plays into this equation, what I think is important is, for this equation, we choose a value of the gas constant and temperature so that these terms are always positive. So temperature in Kelvin, always positive, there's no negative Kelvin.
Right.
Right, so this is always a positive value. This is always a positive value. This thing is either positive or 0. So because of the negative sign, this term is always 0 or negative.
Yeah.
Positive, 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 negative sign, negative.
So increases any of those will cause a decrease.
Right, right. Increase in any of these, typically these two, causes to become more negative, yeah, yeah. Okay, that's important for osmotic potentials. Okay, there we go for that one. Can we get to this? What's important here? Well, we've talked about this. The water flowing through a tube. This equation where the driving force is the gradient in pressure potential. The difference in pressure potential causes that convective flow or mass flow. This difference in pressure potentials. And we can write this. Contrast that to water moving across a membrane where it's the difference. If the reflection coefficient is 1 for all the solutes in the solution, it becomes the difference in the total potential across that membrane that's driving the movement of water across the membrane. Okay. And here's the diffusion equation that I forgot the distance on, where the movement is the difference in concentrations over the distance. So it's the high concentration moving to low concentration. And typically written in terms of the thing that's doing the moving, the thing that's dissolved in the water, not in terms of water itself. Okay, diffusion coefficient. All right, so that's that. What's important here? This was reviewed, right? Okay, so you remember all this stuff. Well, movement of water across a membrane is the difference in total potential, but it's facilitated by channels in the membrane called aquaporins that aid water movement. So that is a way that the plant has to alter its hydraulic properties of the cells, is by changing how many of these aquaporins are put in the membrane. More of them, easier for water to move. Fewer of them, harder for water to move across the membrane. So that is an example. So we have this flux of water where it was L times difference in the total potentials. That is how the plant can alter this term in the equation. By the expression of these genes that code for these protein channels in the membrane, the aquaporins. And aquaporins are ubiquitous. They're all over the place. All kinds of membranes. And we saw this little video where these guys made of water molecules moving through the membrane. Okay, osmosis, you remember all this stuff. Okay. So, there we go. Aquaporins are important because we're getting there. Okay, Heffler plot, we covered this already. Okay, day and night example. Okay, so here is most of a day, of course, of water potentials over a day, pressure potential, total potential, osmotic potential. Here's another example, a little less clear, but again, positive pressure potential, negative total potential, negative osmotic. Here's the pre-dawn water potential coming into equilibrium with the soil, and how the reason that I and many other people consider that pre-dawn water potential a good indicator of the degree of water stress that a plant is experiencing, because that's, over time, that's as good as it gets for that plant. That's where its water potential is closest to zero. And this just shows that. Okay, and here's how, remember this, over the course of a season, is how this pre-dawn value decreases as the soil dries out. Okay. All right. What's important here? Cell expansion, okay. Why cell expansion? Very sensitive to water stress. And when cells expand, a couple of the parameters that affect the rate of expansion. The threshold pressure potential below which no cell expansion occurs, 0 below that. And the cell wall extensibility, how easy it is for a given pressure to push out and move those, increase the size of that cell wall. So the slope of this is the cell wall extensibility. Here's the threshold below which no cell expansion happens. That's important. That gives us one equation here, where the term in the brackets, in the parentheses, is known as the growth effective turgor, the degree to which we are above this threshold. That amount for this cell, for this dot here, that amount is the growth effective turgor for that point. So that's one equation. We already had our other equation, this one here on the board, or up there, written like this, that can be manipulated algebraically to give us a term that involves the volumetric hydraulic conductance of the pathway and what's known as the growth-induced water potential gradient. The difference in the total water potential between the source of that water and the expanding cell. And again, by expressing aquaporins or not, this term can be altered by the plant. The plant has no control over this external potential. It has no control over the pressure component of this internal potential. It can control the osmotic component of this internal potential. So what way does the plant have? Here's a question that could be asked. What way does a plant cell have of influencing this growth-induced water potential gradient? How can the plant change that, given its certain conditions? How can the plant change the magnitude of that term?
By altering the internal osmotic potential.
Yes, by altering, and how does it alter that internal?
It's concentration.
Concentrate solutes or dilute solutes. Yeah, changing the concentration of solutes will make this term more, like if it increases the solute concentration, this term becomes more negative, this term becomes more positive, and this term increases, and vice versa if it dilutes. So there's the way the plant has of altering the growth-induced water potential gradient.
Did we say aquaporins were active or passive?
That's a passive movement of water through the aquaporin. That's a passive, yeah. It just provides a pathway. Yeah, it doesn't speed it up.
It doesn't pump it?
No, it doesn't pump it. No, it just provides a pathway through the membrane, which is mostly, remember on the inside of the membrane, it's mostly lipids in there. And water doesn't want to go into oil. So, but this provides a pathway for water to get through where it doesn't have to interact with, highway, where it doesn't have to interact with the non-polar molecules. Okay, so then we put these two together into one equation. Remember this, I've got this equation here. And this shows how the relative rate of cell expansion depends on a bunch of parameters, any of which can change. Okay, so the volumetric hydraulic conductance can be changed through aquaporins. How can the cell wall extensibility be changed? By the plant. By the metabolism of the cell, yeah. And this extensibility is an expression sort of the mechanical properties of the wall, how easy it is to expand that wall, and that depends on the nature of the bonds holding that wall together between the cellulose fibers in the wall. And so by using enzymes that break those bonds, the plant can alter the mechanical properties of the cell wall, can alter the cell wall extensibility. In the acid-induced growth hypothesis, remember, was that back here? Yeah. It's thought that auxins increase cell wall extensibility by binding with something in the membrane that stimulates extrusion of protons into the cell wall spaces, changes its pH, and activates these enzymes that cleave the bonds in the wall. So auxins are thought to work that way, but however, it is that where is it on here? It's better on this one. By the metabolism of the cell acts to break those bonds, but at the same time, the cell is depositing more fibers on the inside of that cell wall, and synthesizing new bonds, and so it's the relative, these things going on at the same time that determines the properties, and eventually this one wins out over this one, and the cell stops expanding.
Is that something you might ask us to explain?
This?
Yeah.
Probably not, no, probably not. I mean, I don't like graphs like this very much, because they're just sort of I shouldn't say that, they're useful, but a lot of times for me, they're kind of disappointing, because there's so much that's not explained, like metabolism, like, what does that mean? Really? Metabolism in a box? Oh, okay, but there's a lot of stuff going on there. So they're not so satisfying to me, but, and this one's the same way. It just has more boxes, but really, a lot of these aren't expansion control. What does that mean? Just, I probably won't ask anything about graphs like this, or figures. Okay, so we came up with our big equation. We have questions like, that raises questions like this. What happens to the relative rate of cell expansion as the temperature increases? There's a question for you. Think about that. Temperature, you don't see it on here.
It's related to the osmotic expansion, isn't it?
Yeah, so one way it could affect is if we have this equation, right? As the temperature increases, the osmotic potential decreases. This decreases, this term gets bigger, this term gets bigger. On the other hand, it's not so simple, because temperature also affects the rate of chemical reactions, like the cleaving of those bonds in the wall. That's dependent on temperature. Higher temperature, faster reaction rate, which is going to affect this. Maybe the cell wall extensibility, maybe, but on the other hand, higher temperature, faster synthesis of cellulose. So maybe that's a wash. I don't know. So temperature is a kind of a funny one that you'd have to, Maybe it's a good question to ask, you know, to explain your reason for your answer. Could be anything, right? But this one, I think, if I were to have to answer that question, I would start with this, talking about this. So, anyway, but you see some of these other questions that are listed, all right? And then, just finishing up quickly because we're out of time. Talked about this, okay, blah, 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 all these things that don't, osmoregulation, all these things that don't affect. Pressure potential doesn't control. Isn't the reason why cells stop expanding at low water potentials because of this turgor maintenance due to osmoregulation in the expanding zone. But still, the cells stop expanding. Why is it? Because what these guys found, first, when they imposed this dramatic stress very quickly, the first thing that changed was this growth-induced water potential gradient because the external potential decreased. And so the relative rate of cell expansion decreased in concert with that. Over time, that recovered and got even higher than it was, but the rate of cell expansion still was low because by that time, the wall extensibility and the volumetric hydraulic conductance had changed. How can they change? Well, metabolism in a black box alters this and this. But maybe through expression of aquaporins here, and maybe through the enzymes actively cleaving bonds in the cell wall versus the rate of cellulose synthesis that affect this primary. Whatever it was, those things changed in the long term and kept this rate low under these new conditions that are more stressful. All right? And these things. Another, I think the interesting thing here, this growth-induced water potential difference is bigger than the transpiration-induced water potential gradient that's driving movement of water into the, or up through the xylem out to the house. And roots behave differently. The fact that roots behave differently and can keep their cell expansion positive in the face of decreasing water potentials allows the plant to have another strategy for surviving long-term water stress, which is altering the root to shoot ratio, ultimately having a response that ends up with more plant biomass in the root system versus in the shoot system in the face of stress. Increasing the root to shoot ratio, increasing the root length per unit leaf area so that each part of the leaf has more roots supporting that part of the leaf to get water. And so that's the result of not having this root cell elongation go to zero in the face of water stress, even though the leaf does go to zero. All right, so that's the end of that one. And that's it. That's all there is to it. Okay, see you